I want to talk a little bit about using radians to calculate arc length and angular speed of a rotating object. And our basic relationship, remember, is if I've got a circle and I've got a certain angle in that circle, that angle is theta and the radius is r, then the distance, the curved distance along that circle, the arc length, is given exactly by r times theta. That only works if theta is measured in radians. If theta isn't in radians, it's not radically different, but it becomes a more complicated formula that we talked about when we in the last video talking about the conversion between degrees and radians. Well, this is more about once you've converted something to radians, what do you do with it? Well, one of the most basic things to do is to use this equation, and I want to use that equation and a derivative form of it, something derived from it, to talk about arc length and angular speed. So it's one of those equations where you can be given any one of the three and figure out the other. So for example, if I know that the radius of a certain circle is 10 meters, and I've got a portion of that that subtends, let's say, 0.74 radians, then this arc length here, so if that's 10 and that's 0.74 radians, then the arc length, it's very easy to calculate. It's just 10 meters times 0.74 radians. And here's a funky thing about radians. Usually, if you combine two things with units like this, the units of the answer would be meters times radians. And this is something I remarked about in the last video, is that radians are such a natural unit that often people won't even write that down. And there's really good reasons not to write it down, because they really aren't a unit at all. They're so natural that when you multiply meters times radians, you really are just getting meters again. Because remember what theta was defined by. It was really defined by this ratio. So the angle in radians is a distance divided by a distance. The units completely cancel out there. And so you can put radians in at will if you want, if you know it's an angle and you know it's correctly given in radians. But usually people don't even write that. And then the meters just comes through, and it's just going to be 7.4 meters. So you've got some exercises, some pretty basic exercises, playing with this, and also playing with area. And I'm going to go ahead and let you look in the book for the area version. It's really very similar in terms of using these formulas and just getting used to them. I want to focus on a couple of examples where we look at a word problem. And here's one that seems at first to be really different and much, much more sophisticated, which is about a sphere, namely the surface of the Earth. And the question is, here's Albuquerque. Let's say I'm going to draw it sort of edge on. So here's Albuquerque. So here we are in Albuquerque, and what I want to know is how far would it be if I wanted to walk to the equator? How do I do that? I want to measure that without actually going there and doing the walk and taking a big tape measure. Well, what you know from looking at a map, what you can find out from looking at a map, is the latitude. And that's just about 35.1 degrees. And what does that mean? It means that if you go into the center of the Earth and take the angle, the central angle, theta, between a direction to the equator and a direction to Albuquerque, that's going to be 35.1 degrees. Now, this is a two-dimensional surface in a three-dimensional space, but we really just need to look at this circle. The circle that starts at the equator, goes up through Albuquerque, through the North Pole, around through China and Russia and various places, India, and comes through the South Pole and back around. And so we don't really need to use the full three-dimensionality here. It's really about that circle. It's called a great circle. It's what happens if you move up a longitude line around on the Earth. So we've got exactly this situation we had before. We have a theta, which is known from the map, and we can look up r, And r for the Earth is about 4,000 miles. That's not very precise, but it's close enough, and it's what the book uses. And so we should be able to figure out the arc length, s. And so, in fact, s is just going to be r theta, 4,000 miles. Uh-oh. Wait a minute. That has to be in radians. Do not use this formula unless you have already converted theta to radians. So, but that's not hard, because that's just 35.1 degrees times, and then the conversion is pi over 180 degrees. And remember, I could write radians here, but I'm just not going to do that, because I'm going to try and get used to the fact that we don't need to write it, and we kind of shouldn't write it. So that is going to be, let's say I did calculate it this time, and that's going to be 0.61261. And I'll put that in here. And then you multiply that out, and it turns out to be 2450.4 miles. Now, given that this wasn't really to 4 significant figures, I shouldn't report that to 5, but it's about 2450 miles to the equator from Albuquerque. So that's an interesting fact. So that's an example of using this in a real-world situation. Now, I should make a comment about Radian measures. It's similar to a comment I made before about special angles and triangles versus just random ones. Here, this was a totally random angle, even in degree measure. It wasn't a nice number even in degrees. And we multiplied it by pi over 180, and we just got a decimal. Nothing special. But there's certain special angles, like if I have theta equals like 60 degrees, then that's going to be equal to, when I multiply by pi over 180, you can get an exact answer that's really nice if you leave the pi in. 60 over 180 is 1/3, and so it's going to be pi over 3. And so it's going to be pi over 3 radians. And most of the time, we're going to leave it like that. And people tend to get the impression from that, sometimes, that angles in radians always have to have a pi in them, or that the pi is somehow put in artificially. This is still just a number. It's about 1.05 radians. It's just that it's such a special angle in degrees and such a special angle in radians, such an important angle for all of our sort of basic cases, comes from a 30, 60, 90 triangle, etc., that we often leave it like this. Okay, so we're going to have some context-dependent stuff, where sometimes we're going to see radians, angles in radians like pi over 2, pi over 3, pi over 6, things like that, and sometimes we're just going to grind them out as a decimal. And I'll try and give you, guidance as to the context there. But you don't want to think that having the letter pi is synonymous with being in radians. That's not actually accurate. Okay, so now the next thing I can do, I want to do another thing about the Earth. We'll probably have to spill over into another video, but it won't go for 10 more minutes. I want to think about the fact that the Earth turns on its axis. Okay, and therefore any point on the Earth is going around and around every 24 hours. Now let's look at a point on the equator, just to be simple. That guy's going to be moving towards the east at probably a pretty high rate of speed, because the Earth's a big thing, and it only takes 24 hours to go around. So how fast does a point on the equator move? And there's actually two different versions of speed that we could ask about. In 24 hours, we go this point on the equator. Hello, it executes 1 revolution, and that's equal to 2 pi radians. And the measure of how much angle you do in a certain time is actually a very useful thing to tell how fast something is rotating. So there's a couple ways to say it. We could just say 1 revolution every 24 hours. That's a measure of angular speed. It doesn't tell you anything, it doesn't have anything to do with how big the circle is that you're going around. It just tells you how many revolutions per unit time. And that's often called by little Greek omega. It looks like a W, but it's curlier, and you should distinguish it from a W. That's omega. It's a small, lowercase omega. Okay. And we could also say it's 2 pi radians. per 24 hours. And let's get a decimal on that in the next video.